In this video, we are going to look into some of the common questions of general theory of relativity. Questions like, why will I study relativity? Will it help me anything in my career? Will it help me in getting a good and a secure job? What is the use of learning relativity? All these questions and more will be answered in this particular video. These questions arises when you're studying relativity, or you're thinking to study relativity, or you have something in your mind to carry on specialization into general theory of relativity. So this video will be answering all your common questions as well as take you something which will help you in your career and job prospect, as well as clearing out most of the common misconceptions which you have. My name is Shaunak and you're watching this video on Physics for Students. I heartily welcome you to my channel. So before we start and go ahead with the common questions of general relativity, let us see what are the topics that we are covering. So we are covering these questions and something more. We are going to look into general relativity with a different kind of a definition. We will also know that whether it is possible to learn general theory without learning special theory. What would be the approach if I at all think of learning general relativity? Can I learn general relativity all by myself? Can I be self-taught? What are the level of mathematics that I need to know? Why do we need tensors? Can we learn relativity without tensors? What is called a parallel transport and what are geodesics? Do we really need to learn differential geometry, or we can skip differential geometry to learn relativity? Will this help me in anything in my career or job prospect? And what are the practical applications that deals with general theory of relativity? These are the questions, and these are the most common questions. Apart from that, if you have any question, please feel free to comment in the comment box. I will do my best to answer your queries. So first, we will look into general relativity, a little kind of a different definition, not the usual one. Now we know that it is a geometric theory of gravitation which was developed by Einstein and others. If you have seen my other videos, I have mentioned a detailed history how his friends, including Michel Besso and Marcel Grossman, helped him to develop this theory. It was developed and it was published around 1915, although it was developed much prior to that. And what it does is that it refines and generalizes special theory and Newtonian mechanics in different ways. So we see that good old Isaac Newton's rules of gravitation or the laws of gravitation is getting generalized into what we call a curvature of space-time. So right on your screen, what you see is a space-time manifold, or which is called a rubber sheet geometry, and the ball which is causing a dent is basically causing a curvature. And as you can see, the sun has got a lesser curvature, white dwarf has got a more curvature compared to the sun, neutron star even has a greater curvature than white dwarf, and black hole has got the extreme curvature. So if we start with Newtonian mechanics, then we develop a space-time manifold, and these actually helps us to do a lot into cosmology and learn what is the space-time curvature and do into more into exotic matters like neutron star and black hole. In general theory of relativity, we know that straight lines are basically generalized more into geodesics. So what we used to call classically straight lines are now called geodesics. The concept of space and time, which started from the time of Descartes or maybe even prior to that, which Newton and other classical determinism dealt with space and time is something different, has been united into a space-time kind of a lump which was developed in early special theory of relativity and which is developed and refined more into general relativity. The entire definition of space-time manifold curvature is being described in this, which is called the Einstein's field equation, and this Einstein field equation predominantly consists of tensors, and we will see that why do we need to learn tensors. The entire relativistic theory helps us to develop more avenues and more areas into cosmology, black holes, gravitational time dilation, gravitational waves, and now we are working on dark matter. So all in all, this is a general idea, just a picture to give you an idea of what general theory of relativity is all about. But hold on, there is more to come. So we know that the Newtonian and classical mechanics that we were studying, which includes objects like momentum, velocity, force and energy, vector and mass, and motion and acceleration, is being generalized by Einstein in his special theory of relativity. So this is more of a generalized form of the classical Newtonian mechanics, which is further generalized into general theory of relativity. So it is a process of generalization from one part to another. So we give a green tick mark with special theory of relativity, and general theory of relativity is a much more refined version of the classical deterministic world. Starting from Newtonian mechanics, the entire elements of force, etc., are being dealt into generalized form in special theory, which is being further refined into general theory of relativity. Now here is something very interesting. Special theory of relativity actually deals with inertial frame of reference. It deals with speed and velocity. Most importantly, it is experimentally provable, and it also has something related to frames of reference. When I'm telling experimentally provable, note that I am not saying that general relativity is not experimentally provable. What I'm trying to tell is that on a much smaller scale, the special theory of relativity is experimentally provable, and we can develop those kinds of instruments to prove it. General theory of relativity, on the other hand, deals with non-inertial or accelerated frames of reference. It is something which is related to gravity, which is further refined as geometry of space-time, and it is on a much larger scale, on a cosmological scale. All those equations and the calculations take place. So special theory of relativity deals with study of relativity and simultaneity, and that is why it deals with speed, time and space. Where general theory of relativity, instead of calling general theory of relativity, can be called as a theory of gravitation or theory of geometry of curved space-time, and hence it is dealing with surfaces and curvatures. This is a kind of a vis-a-vis that why general theory of relativity, rather than calling it a theory of relativity, I think that it will be wise if we call it a theory of curvature or a study of geometry, because it has less to deal with relativity and it has more to deal with curvatures and geometry. The relativistic part is mostly dealt with special theory and less in terms of general relativity. Okay, so we come to the next question, which is very often asked among the students, that can I learn general theory without learning special theory of relativity? Now here there are two parts. One is a no and one is a yes. Now I will tell you what I feel. So if you go to the no part, I mean to say those who are telling that no, you cannot learn general theory without special theory, you need to learn special theory first. They are following a conventional approach, because initially it starts with the inertial frame of reference, then it moves into non-inertial frame of reference, and it is the understanding of the basics first. I mean to say the mass energy equivalence, the equivalence principle, the Lorentz transformation, the Lorentz force, everything actually starts with a special theory. And it is easy because any high school mathematics, you can understand special theory of relativity. Now coming to the general theory, it is totally an independent theory. As I told you, it carries more and more into the geometry of space-time. Second, it is an independent approach. That means you can attack or you can learn general theory without the initials, just on a sense that it is taking up as an independent approach. It is definitely a theory of geometry, and it has many branches of mathematics, which we will soon see. And yes, we can learn with a geometric approach. That means special theory is more into simultaneity and inertial frame of reference, whereas general theory is more into geometry of space-time, and it contains different branches of mathematics, and it can be learned with a geometric approach. Now there are certain people who might say maybe, but we being physicists and learners, we are not dealing with the maybe part, but so we should either deal with no or with yes. Okay. Now, whenever we are learning a general theory of relativity, for the students especially, or those who are starting with undergrad, it is a very common question, what is the approach that we should take? Now, what do I mean by approach? Most of us, I mean to say most of us who are very passionate about relativity and we are starting to learn general relativity, we take an intuitive approach. There are books, materials, stuffs in internet lectures which claims that yes, you can understand general relativity on a very intuitive approach. The problem is that if you take an intuitive approach, you're going to land up with a lot of misconceptions. Also, you will learn not the mathematics part, and most importantly, you will remain in the virtual reality world, which would lead to wrong concepts. As I always tell, that physics or mathematics, physics especially, it cannot be done just on a virtual or a intuitive approach. We need to learn mathematics, because mathematics is the language of physics and the language of the world. So intuitive approach is very wrong, and I would say let us not take this approach. The next approach which comes on the right hand side is called the pure mathematical approach. Now, there are certain pros and cons into that. The first is that if you take a kind of a pure mathematical approach, it will definitely going to take more time. Why? Because we need to build up on the basis of mathematics, build up on the basis of different branches of mathematics which relativity deals with, and it will take a huge amount of time. You need to have a very good subject knowledge, I mean to say the knowledge of those branches of mathematics. And it is not good for starters. I mean to say you will lose interest. The mathematics is difficult and too vast. So I mean to say it might not be some very good for starters. And eventually, if it takes for such a long time, you're going to lose the interest. However, I would say yes, if you are taking a pure mathematical approach, then definitely it is the right approach to learn relativity. I would suggest let us take a middle path. This middle path actually is something where math becomes clear. It is less arduous, it takes a moderate time, and it helps in developing a liking towards the subject, and this is called mathematically intuitive approach. This is the approach which I take in all of my videos. Neither I take a pure intuitive approach nor I take a pure mathematical approach. Rather, I take a mathematically intuitive approach. That means some part of the mathematics, some part of the intuitive joined together. It gives a very good and a clear understanding of general theory of relativity. So if you are stuck up with the question, or you're thinking in your mind, which way shall I go? Shall I just read the common fictional books which leads to romanticism? No. If you're going for pure mathematics, yes. But again, if you're not that good in mathematics, or you're thinking to learn in a relatively shorter time, you should not take the pure mathematical approach. Rather, let us take the middle path, which would lead us in a less time, but with a good knowledge of mathematics, a mathematically intuitive approach. Okay, so the next question which comes is that, can I learn general relativity all by myself? Those who are self-learners, who are learning through videos and websites, this is a very common question. My answer to the question would be yes, but there is an if factor. The if factor leads that you really know differential calculus, integral, multivariable calculus, linear algebra, a good amount of tensor calculus. You really know what are the applications and usage of differential geometry. You know what are the curvatures are and how the tensor deals with it, which will eventually lead to Riemannian geometry. You understand the equation of geodesics, the formulation of Lagrangian, the Cauchy and the Regge surfaces and calculus. So I would say you can learn if you know all those mathematics very well. But still, I would say that verify your learning with somebody who is an expert on that, possibly a professor or a teacher or somebody whom you can go and verify. Because in my case also, with years of experience, still I make mistakes. Still I go to my professors out there in US or in India and try to consult that whether my understanding is at all right or not. So yes, you can learn it provided you know those mathematics, but again, I would strongly suggest that get hold of a professor, get hold of a teacher who will verify, yes, I have learned whether this learning is right or not. Okay, what mathematics do I need to learn general relativity? Now, this is a very broad question. If you can go back to my playlist in general relativity, you will find how to learn general relativity. I have made 2-3 videos on that where I have clearly laid out what are the books that you need to know, but this is a good time when I can tell you what are the mathematics which are required. First of all, you need to know multivariable calculus in a very strong manner. I assume that you already know the basic calculus and integration, but these would lead to partial differential equations and multivariable calculus. You have to know linear algebra, because linear algebra is the core of the metrics and the tensors which will come upon. You have to have a very good understanding of vector calculus. You need to know the classical Euclidean geometry. Otherwise, you won't be able to understand non-Euclidean geometry. You also have to get a very good understanding of tensor analysis and tensor calculus. And the most interesting and the demanded subject, yes, you need to know differential geometry, which will eventually lead to what is called Riemannian geometry. So these are the mathematics, very grossly I have told, but this is not an exhaustive list. Go to my videos, How to Learn General Theory of Relativity. There are enough amount of books, suggestions, and the level of mathematics are dealt in much details. These would lead to some of the primary concepts that you need to know. Time and space-time, you need to understand what are the frames of reference. You also need to understand a lot about coordinates transformations, because remember, in general relativity, we are moving out of the flat space-time and going to curved space-time. So all these transformations from flat to polar, spherical, hyperbolic transformations are required. You need to have a clear understanding what are the postulates of special theory of relativity. You need to understand what are space-time diagrams and a lot of curvatures. And you have to visualize how the change in frames of reference really happens. Because general relativity is all about curvatures, all about shifting from the classical Euclidean and Cartesian coordinates to other coordinate systems. Okay. Now this is a very common question, that why do we need tensor, or at all do we need tensor? I would like to answer to this question that, for example, on the right hand side you see it is a flat space and we take a vector A and we try to measure this vector A with AY and AX as the components of the vector, and we find this blue dotted line which shows the components of the vector. Now we take another curved space-time, so this X and Y in gray, we now plot it in here. These are the X prime and Y prime are the two curved spaces, and the vector and the length, everything remains the same. And now we try to measure the components of the X coordinate system, which is A prime X, and Y coordinate system as A prime Y. Now once we join those lines with these blue dots, what we get is that A prime X is definitely longer than AX on the right hand side, the original quadrant, and A prime Y again is longer than the original A prime AY in the right hand side quadrant, and most importantly A remains invariant. So you see, the basic point is that if you're moving from a flat place to curved space and we are measuring the same vector from flat to curve, we see that the components of the vector changes. And that is why we need tensors in general relativity. You see, this is a curved space-time, and I will place certain balls, spherical balls over here, and you see that the curvature has got different types of curvature, right? So simple presence of mass, yes, causes the space-time to distort, and that the basis of vectors change. So we need tensors, yes, because tensors retain the original form. As you have seen, the original A vector remains the same, which is the whole point of relativity. In general relativity, tensor obeys a rule which is called diffeomorphism. I'm not going to discuss. You can look into my video on topology where I have explained about diffeomorphism and homeomorphism. Tensors, yes, they are the transformational properties which are encoded within them, and they are essential in writing general relativity equations. They are coordinate independent system. You can think it of a space-time just as a rubber sheet which is undergoing stress and strain, and tensors describe the material stress or strain. So this makes the basic concept clear that yes, we need tensor, otherwise how will we measure the change of the basis of vectors from one coordinate system to another? So tensors retain that equation or the original form of the coordinate system, and when it changes, we can still do measurements, we can still do calculations, but retaining the form in the coordinate system, and it becomes something which is called coordinate independent. There's a small thing which is called, which I would like to tell you, is a covariance tensor, which means covariant, which means changes in the same way. So if you're measuring V in this direction and there is a change, you can imagine the change just as I've shown, it will be in the same way. So distance of the vector remains the same, that is, it is covariant, it is going along with something. Co means somebody who is going along with you or in accompanying with each other. There is another type of tensor which is called contravariance tensor, where it changes in the opposite direction. So if I'm measuring v in this direction, either it will be in the opposite or it will be measured more than that. So you see the distance of the vector here is doubled, where in covariance it remains the same. So if you want to know really more about co and contravariant tensors, you can look into my tensor analysis into my playlist. I have got many videos which speaks about co and contravariant tensor in a much more bigger, in a detailed fashion. So I just wanted to tell you these are the two technical terms and very important to tensors. Now we come to the central part. Do you see this? I know you recognize it. Yes, it is Einstein's field equations. Now the entire Einstein's field equation revolves around tensors. There is something which is called a Ricci curvature tensor, which measures the volume of matter as it changes from flat to curved space. There's something which is called a Ricci scalar, which keeps track of how the size of a ball which deviates from Euclidean space. There's something which is called metric tensor, intrinsic default tensor, which measures the causal structure of space-time. We also have Riemann curvature tensor, which is a tool to describe the curvature of Riemannian manifold. And finally, the stress energy momentum tensor, which measures the matter movement through space-time, which is responsible for causing the curvature. Each one of these aspects, Ricci, scalar, curvature tensor, metric, everything has been dealt in detail component by component in my other videos. You can watch it in my playlist in General Theory of Relativity. I wanted to show you because if you take the entire field equations, except this 8 pi c4 and the lambda, all of this and the g gravitational constant and c4 being the speed of light, all of this revolve around tensors. So yes, the tensors are the heart. It is the central centrifugal force which keeps the general theory of relativity alive. So for curved surfaces, we have gravity field equations. We know measurements are not orthogonal, that means not perpendicular. We need tensors. We have to frame a new geometry, so we called it as Riemannian geometry. Once we move from Euclidean to non-Euclidean, we need differential geometry. And the principle of general covariance, things will change along with the measurement. That is why we call it covariant theory of gravity. Okay, now we come to another important question, a very important concept, I would say. What is parallel transport and how it leads to curvatures? Now, parallel transport is a very simple concept. If I am trying to measure one vector, whether it is smaller or bigger, what we do? We just transfer that vector over the other. As you can see here, these two vectors, one is bigger than the other, whereas this vector is smaller than the other. How do we recognize? We just slide one vector over the other, and if it matches, then it is called that this is the same. Otherwise, it is either bigger or smaller. Now, it is a way of comparing vectors at different positions in the manifold. It's a way of transporting data along the smooth surfaces in a manifold. Now, let me show you one simple example of parallel transport which deals with flat space-time. So this is a kind of a triangle, right? And this red dot and this yellow arrow, it denotes that we are going into this time. And we will keep on moving this vector provided that we do not change the orientation. So it moves here, it moves here, it moves here, further it moves here, then it comes here, then it comes here, and finally you see that the black arrow or this black vector exactly overlaps with the other. So what does it mean? It means that in flat space-time, when we do a kind of a parallelly we are transporting without changing the orientation, the vector, if it matches and comes back to the original space, we call it has been parallelly transported. But the question is that can we do the same experiment on a curved space-time? So here is a curved space-time. It is a sphere and I'm standing right on the North Pole, and this is the red dot which is signifying that I need to move here. And I'm using this again, the same yellow vector. I'm trying to move towards this blue vector, keeping it the same. So I mentioned the original vector as v. I'm trying to keep it straight, but you see eventually it rotates, it moves. So this curvature along this surface is because the vector has moved to purple because of the curvature. Now from this blue vector, I'm trying to move over here. Can I do keeping the vector the same alignment? It comes over here, it comes over here, it comes over here. And now from here, I want to move to the North Pole as shown in the green arrow. And I trying to keep this vector same, but eventually it has come to this yellow, blue, the center one, right? So it is the V prime, that is the vector which we started with V moving along the sphere eventually has changed its direction. So now if I take out these two vectors, we find there's a significant difference between P and V prime. And that is what is measured by the Riemann curvature tensor. So the Riemann curvature tensor describes the change of all the components of the vector in the space-time direction. This is actually the Riemann curvature tensor. I'm not going right now because I've got a separate video dealing with Riemann curvature tensor. Let us understand that we are dealing with parallel transport. We are trying to parallelly transport along the sphere and we find there is a difference. So what do we find here is that the Riemann curvature tensor which we deal with now gives a complete description of tidal forces in general relativity. So we go ahead with this photograph or this illustration. And now what we are trained is that parallel transport tries to keep the vector constant as much as it is possible, but it is not possible. So the parallel transport cannot keep vectors constant. In order to do that, we need a separate item or a separate concept, mathematical concept, which is called covariant derivative. I'm not going into this. The covariant derivative, just to tell you, looks like this, that this nabla sign of this U, it denotes the direction, and B is the vector field. And what it does is that it shows the rate of change of a vector field. So covariant derivative is a correction tool which helps us to find parallel transported vector fields. So that brings us to the understanding that why it is meant by parallel transport. We are trying to move along the vectors around the surface in order to get back to the original, but somehow we are unable to do that. That means it is not being parallelly transported, and we need a tool to correct that, which is called covariant derivative. Okay, so we come to the next question, very common, that what actually are geodesics? Now, just to tell you, geodesics are nothing but straight lines. So we have got 2 points and we join it with the red line, and then we get this kind of a shape. There are 2 points, we join it by a red line, and then we get a kind of a curvature. Here there are 2 points and we try to join it, but it gets a little bit curved. So what do I mean by that? Here also we see that these are curvatures, right? So this comes to a famous analogy used by the great Professor Amol Kumar Chaudhary, that if you see a tram and it is given to move along a tram line, if you ask a physicist to tell where will the tram go, he will do calculations on the initial conditions and given two variables using Newton's F equals to ma. But if you ask a rickshaw puller what the tram would lead to, he will say this, that the tram will exactly move in the path which is laid down. So this leads to a very simple definition of geodesics, that geodesics are simply the shortest path between 2 points. So these 2 lines are being generalized into a curved space, a curvature. So that generalizes the notion of lines into a curved space-time, and this curvature is due to the curved is due to the gravity, is due to this curvature of space-time, and what causes this gravity is due to the stress energy momentum tensor. You can look into stress energy tensor if you really want to know more. That is covered in this separate video. So an object moves through space-time in a straight line, just like the line will follow the curvature and may change the direction if the curvature if the curvature is done so. So gravity is actually due to this curved space-time, and the source of this gravity is stress energy momentum tensor. So this effect, this bending effect, is what we call gravity. So just to illustrate a little bit more on geodesics, you see these are the 2 parallel lines, and just you have to ignore what is called S-vec, that is separation vector with the Ricci tensor. But just remember that when things are parallel, the geodesics are parallel, it is 0. You can have this kind of a geodesic which are converging, so you get a kind of a positive curvature, and when it is separating, you get a kind of a negative curvature is less than 0. You can also think of geodesics something like this. Okay, so what we are going to do is that we are going to move this ball along this line, and these are the separations, and we see that the ball has uniformly moved, so the sectional curvature is 0 and the size of the ball remains the same. So this is one type of a geodesic where the ball remains the same. Now this type of a geodesic, right, you see it is converging. So if I take a ball around here and I try to move the ball, what will happen? It will shrink in size. So you see here it shows that the size of the ball shrinks. And if we get this kind of a geodesic, if we take the same ball and we're trying to move, what happens? 1, 2. So what happens is that the size of the ball increases. I'm not going to further details of sectional curvature, etc. But try to understand these three types of geodesics actually are different paths in space-time, and the size of the ball, you see the first part, it remains the same, the second one shrinks, and the third one increases in size, and that is why it is the effect of geodesic. Okay, coming to the next question, do I need to learn differential geometry? The answer is obviously yes. Let us see why it is. Suppose we are standing on this curved space-time, right? Here I am trying to move from here to here, and again I make a movement from here to here, then I move from here to here, again I am moving from here to here, and finally somehow I end here. The same thing what I do is that I try to plot this sphere in a curvature, right? And I do the same thing. I'm moving from these points 1 to 1 and 3, 4, 5, and then finally I end up here. So do you notice something very interesting, that the sphere which looks like a sphere, when I'm looking from maybe outside the sphere, I'm located in space, I'm looking at it. So but in a curved space-time or in a curved Euclidean space, this one locally resembles Euclidean space near each point. That means this is global and this is local. What does it mean is that this is differential geometry. Differential geometry will do something that will locally make the sphere look into local Euclidean space. So that locally resembles Euclidean space near each point. This definition is called a manifold, which is locally Euclidean. This is a manifold which has got a neighboring point x1, x2, dot, dot, dot going up to xn. And Euclidean Cartesian space is the space of all real numbers, which is denoted by this. So a locally Euclidean space topologically looks like this, which is R of n. This is local and this is Euclidean. So differential geometry, we will make the entire global surface merge or look something into local. Now the question is that why do we need local? This is being dealt in this part of the video. So you see we have got a sphere and we draw lines, it converges. We have already seen geodesics. It is called positive curvature. In this kind of a cylinder, there is no deviation, nothing. It is zero curvature. And I think this is hyperboloid, if I'm not wrong. It leads to negative curvature. Now all these curvatures, when we are trying to measure, what will we do? Obviously, we will apply the rules of calculus. So here I have broken down the manifold, that is the curvature, into this, right? So here what I'm doing, I am sectionally dividing infinitely this curved surface, and I can apply dy by ds, that is calculus. So applying the rules of calculus on the manifold directly from the differentiable manifold of the surface. This is the rule. This is what we need to do in differential geometry, because general relativity is all about curvature of space-time. And how will we measure using the different rules of calculus? That is called differential geometry, when we are applying the rules of calculus in geometry. So these yellow surfaces right on the box, this looks like ordinary Euclidean space, and it helps us to do calculus on this space. So we can say that these yellow surfaces emerging right here, these can be mapped into Rn. That means this part is locally isomorphic to the Cartesian space Rn. So a manifold, which is a space, I have shown you this sphere and this hyperboloid and cylinder, when it is broken up and we are using the rules of calculus, that means it is called locally isomorphic to Rn. So this is the surface we can perform differential calculus. So differential or differentiable manifold is something which has got a differentiable structure. So you see I have used D just to denote that yes, we use calculus. This differentiable structure is a differentiable structure on a set M, which makes we can do differential calculus. Let us not go into much into differential manifold. It's not the subject of the video, but just to let you know that yes, answering to the question, we need differential geometry. One thing which is very important on internet or on your books, you must have seen this kind of a photograph. This one, causing a dent in space-time, the Earth and the Sun. What does it actually mean? So if I divide this manifold, this is basically a differentiable manifold. That means a manifold which can be differentiated. Why? Because we need to use calculus to measure it. These dents, as you see, the Earth has got a lesser dent because of its heavy mass, and Sun has got a bigger mass, so it causes more of a space-time curvature. These are the curvatures. And these lines, as you see, the white ones, these actually shows that these lines are denser over here and lighter over here. That means if I'm standing over in the denser line and I'm standing over in a line which is not that dense, which are loose, these are actually being measured by the geodesic path, right? And these tensor lines, etc., are being calculated using metric tensor. So I hope now once you recognize or you see this video, this photograph or illustration on over the internet or video, you can actually understand what does it means. A differential manifold, the curvature, the lines, the geodesic path, and everything is being measured by metric tensor. Okay, now we come to the most important thing which I think you will be waiting for. Will this help me in my career? Now the question is that what are the career opportunities in general relativity? Okay, now first thing that you need to understand is that general relativity is nothing that yes, I have got a job. Okay, I get a degree in general relativity and I walk tomorrow and I get hold of a good handsome salary with a huge amount of dollar. So it is not that it is something which will immediately give you a job. What if I ask you that will I get a job if I learn algebra or trigonometry? So what would be your answer? I hope you understand the point that I'm trying to make. So general relativity will help you to learn much more advanced mathematics. It will help you to imagine about abstraction. It will also help you to think out of the box thinking, and it will help you to enable complex calculations, and you will be helping yourself to think on a cosmological scale. So now you understand that if you do advanced mathematics, what will happen? Abstraction gives, I will show you one by one what would they mean. So the career opportunities are immense, huge in general relativity. But let us not ask this question that if I get a degree in general relativity, tomorrow will I get a job? It is something like asking if I do trigonometry, tomorrow will I get a job? So 1, 2, 3, 4, 5. These are the 5 points you have to keep it in mind, that these are the things that you will learn. Now let us see that what are the opportunities in general relativity. First of all, it will increase the power of your imagination. This is called abstract thinking. Now this would eventually lead to engineering, nuclear physics, cosmology, and quantum mechanics. Try to understand that when you are trying to imagine and your power of imagination is increased, definitely much more complex things in nuclear physics and cosmology you will be able to do. Because you cannot see something like an atom, neither you can see a black hole, neither you can see the spin of an electron, right? So with the power of imagination, our physicists and scientists have done that. You are also going to do. The second thing is that you will understand a lot of patterns and structures which will eventually lead to designing, structuring, and architecture. I know a few of my friends, Gagandeep, etc., who called me after listening to a few of my lectures in differential geometry and general relativity, that they are using differential geometry, which we will see in the later part of the video, in order to do great architecture, beautiful designs, buildings, etc. Third part is that you can create generalized structures on a broader role. So as you understand, general relativity is all about generalizing a single equation into much broader sense, which will obviously lead you to a database administration. You can do a good amount of machine learning, artificial intelligence, and most importantly, quantum computing. These are all related to something which we call generalizing on a small scale to a larger scale. You will also have the ability to link geometrical representation. Very important, because space science, deep learning, computer science, networking, designing, AI and cosmology all are related to geometric representation. You can think one by one how space science, the designing, deep learning, most importantly, network designing are all done using geometrical and neural connections, especially artificial intelligence and cosmology. You will also develop a mathematical intuition which will lead to research analysis, computation, handling large-scale data. So if you develop a mathematical intuition, I mean to say, you can just see an equation and you can tell that what could be the possible way to solve, then definitely you can handle much larger data and you can do much better research and analysis. This is the virtue of abstract thinking in general relativity. I will come to the second most important point, which is the tensors. You will learn a lot about tensors. Tensors are useful in engineering, in elasticity, also in calculation of deformation of elastic bodies, which leads to electrodynamics. Continuum mechanics, solid state physics will also include tensors. You can learn all engineering analysis, fluid mechanics, if you are dealing with materials, how to calculate the stress inside a material, and most importantly nowadays diffusion tensor leads to much better medical treatments which the doctors are using to generate MRI scans. It is definitely useful for wireless communication and mobile computing. Now I can really show you each and every aspect how tensors are being used. For that, I think I can make a separate video on the applications of tensors in real life. So you will learn much more tensors in general relativity compared to any other subject in physics. So if you're learning tensors, these are the options, these are the career opportunities which you can go into. Now, coming to the most important part is that you will learn differential geometry, and it would lead to a huge amount of career opportunities. First of all, you will learn electromagnetism in differential form. You will also learn robotics because it controls nonlinear system. You will learn quantum field theory. You can do econometrics. You can also do modeling of cell membrane. I'm coming to that, very important and interesting. You can also do a good amount of digital signal processing in engineering. You can also do probability using various structures of Riemannian manifold. You can also do what is called structural geology, or to understand the geological structures. And most importantly, you can use differential geometry, which is the Ricci flow, which is already being done to prove the Poincare conjecture. So a big amount of career opportunities waiting for you if you learn differential geometry. And learning differential geometry can be done independently, but GR gives you a very interesting context and to learn more important. Okay, this is a very interesting publication of A.M. Findlay and et al. It is Application of Differential Geometry to Molecular Genetics, published in 1985. And I would like to read a few lines from this. It says that a mathematical formalism is presented in which changes in information content of an evolving DNA molecule may be described. The basic construct is a 65-dimensional differential manifold in a coordinate structure such that the manifold points represent 1. The number of each codon type in a DNA molecule, and 2. The evolutionary time of that DNA. It is shown that this manifold cannot be Euclidean but must be taken at least conditionally to be Riemannian. Evolutionary motions in the informational spacetime manifold are initially postulated to be geodesics, and evolutionary equations of motions are elaborated. So now you see that how these scientists are using differential geometry to molecular genetics. I don't have to learn anything more. Coming to the last part of our video, what are the practical applications of general relativity? Very pertinent and important question which keeps you busy. So first of all, definitely it has given us a whole new understanding of the universe. From Newtonian gravity, we have moved into space-time curvature, and as a result, we have got a lot of cosmological applications, gravity, redshift and blue shift and everything. We have understood black holes, neutron star and wormholes and other concepts of physics much better through general relativity, and it has given us tools which JWST is using for precise measurements on a cosmological stage. On a cosmological stage. So yes, a whole new universe is revealed in front of us through the practical applications of GR. The second thing which I would like to tell is what is called a gravitational lens. Now, Einstein's general theory of relativity describes how mass concentration distorts the space around them. You know that a gravitational lens, which is the best example, is our JWST. It occurs when a huge amount of matter, like a cluster of galaxies, creates a gravitational field that distorts and magnifies the light from distant galaxies that are behind it, but magnifies the light from distant galaxies in the same line of sight. So it allows researchers to study the details of early galaxies too far away to be seen with the current technology and telescopes. It's a big application of gravitational lensing. The simplest of gravitational lensing occurs when there is a single concentration of matter at the center, such as the dense core of galaxy. So the first practical application is a complete new understanding of the universe, and the second one, gravitational lensing. The next one, very important, is called gravitational redshift. Einstein's theory of relativity predicts that the wavelength of electromagnetic radiation will lengthen as it climbs out of a gravitational well. Photons must expand energy to escape, but at the same time must always travel at the speed of light. So this energy must be lost through a change in frequency rather than a change in speed. And if the energy of the photon decreases, the frequency increases. This corresponds to an increase in the wavelength of the photon, or a shift to the red end in the electromagnetic spectrum. That is why it is called gravitational redshift. Yes, we have got a whole new understanding of black holes and other compact objects. Singularity, last year Roger Penrose got the Nobel Prize in Physics to show singularity, and approaching general relativity on a topological and a geometric point of view. Definitely the black holes and the implications, the black holes which is discovered at the center of our galaxy, Sagittarius A star, all these are leading because these are the practical applications of general theory of relativity. We come to the last point, which is called global positioning system. Very important. It is an array of 24 satellites which describes an orbit around the Earth of radius of around 27,000 kilometers and are 7,000 kilometers apart, and every 12 hours at about 4 kilometers per second. Each satellite which we are watching on our mobiles and Ola cars and Ubers, they carry an atomic clock, and the purpose is to locate any point of the Earth's surface. As predicted by Einstein's theory, clocks under the force of gravity run slower rate than clocks viewed from a distant place and a weaker gravity. This means that clocks on Earth observed from orbiting satellite runs at a slower rate. So to have the high precision we need for GPS, this effects needs to be taken into account, or there will be small differences in time that would add up quickly, giving to inaccurate positions. So these are few, and there are many other practical applications of general theory of relativity, I think, which will make your life more interesting to study general relativity in the near future to come. So just to summarize, we have answered almost all the common questions of general relativity. I would welcome you. If you have any question, please don't feel hesitant. Please ask me in the comment box. Do like, subscribe, and click on the bell icon to get all the notification from Physics for Students. In the next video coming up, I will be talking about the mathematics of general relativity. I will take up few of the most important equations of general relativity, and I will explain them, what do they mean and what they can be used, and further details on that. So until I come up with the next video, which is coming up very shortly in this channel, Physics for Students, stay tuned. I hope you like this video, and I will wait for your comments and any question that you have on general relativity. You are welcome. The next video coming up would be the mathematics of general relativity. Till then, wishing you all the best in your future endeavor. This is Shauna signing up from Physics for Students, wishing you a great day ahead, a great prospect and a career in physics and mathematics, and promising you to come back soon with this video, the mathematics of general relativity. Till then, goodbye, best wishes, and stay safe and stay happy.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor at physicsforstudents.com. Stay safe and happy.